Hi all, welcome to the pre-party for Monday, October 14th. It's exciting because we get to start a brand new unit and we are going to talk about seafood for the next week. Now I say seafood ... lipids today because we have to set the stage before we get into actually talking about fish, crustaceans, and how they relate to our diets. As a review, I just want to make sure we're all on the same page. We have been talking and incorporating macronutrients into our discussion of breads, mainly cereals, grains, and baked goods, also into beverages. So in the last couple of weeks, we have talked about two of the macronutrients. Those would be carbohydrates and proteins. Today, we're going to add the third macronutrient, kind of wrap up the discussion of our three basic macronutrients. In doing so, I want you to keep in mind the comparisons and the contrasts between our carbohydrates that we have talked about and our proteins that we have talked about. So remember that carbohydrates, the basic structural unit of any carbohydrate, is a monosaccharide. Monosaccharide meaning a single sugar molecule. I've put up there glucose because that's often the one we are talking about. It's the most important for an energy source for us in our body. But there are actually three monosaccharides. We've talked about two of them. The third one's going to come at the very end of the semester when we start talking about milk. Then when we think about protein, we are thinking about the basic structural unit of an amino acid, and I've given you a basic amino acid. Remember, it's a central carbon surrounded by an amino group, a carboxyl group, and an R group will change based on if we're talking about valine versus tryptophan versus phenylalanine. So proteins and carbohydrates are the macronutrients. Each have their own basic repeating unit, and those units provide structure to carbohydrates and proteins. Now we can add the third macronutrient, and that would be fats. A more general term would be lipids. Lipids include anything from fats, oils, shortening, cholesterol, and so you've noticed that I have three bolded words there, one being phospholipids, another sterols, and another triglycerides. So if we're thinking chemical or structural composition, those three bolded types of lipids are our three main types of lipids. Then from there, we can make things such like fats and oils and shortenings, okay? So in comparing fats, carbohydrates, and proteins, we see that fats are made up of carbon, hydrogen, and oxygen atoms. That should hopefully ring a bell, and that makes them similar to carbohydrates. They're somewhat similar to proteins because proteins also contain C, H, and O, but they also have nitrogen and sulfur often included in them. Nitrogen for sure from that amine group. So chemically, they are similar. However, how we put that carbon, hydrogen, and oxygen atom together to make a structure is very different in lipids than it is in carbs and proteins. The fats or the lipids that we're talking about, the basic structural unit, it is not a polymer. And by polymer, I mean we can't take one structural unit of a fat and link it together to another and to another and to another to create a chain, a connected chain of these structural units. We can do that in carbohydrates where we take a sugar molecule and combine it with another sugar molecule to make a disaccharide and keep creating those links of sugar molecules to make many types of carbohydrates. Same thing amino acids. If we take one amino acid, bond it with another amino acid, we are starting to create primary structure of protein. That is not the case in lipids, and you'll see why here in a couple minutes. Lipids do not provide structure. Now, I should have put an asterisk there because the type of lipid could create some characteristic of structure. It could help build some type of food, and I'm particularly thinking about meat and marbling. But it does not provide structure in the same terms as, say, starch provides structure for a bread dough, or gluten provides structure for a bread dough, or amino acid change provides structure, secondary and tertiary structure of proteins. And then also we cannot dissolve fats in water. This is probably a familiar property to you. If you mix water and oil in the same container, they would not mix. You would see little pockets of oil floating around in that water. If we mix carbohydrates in water, we see dissolving. If we mix proteins in water, we often see dissolving. Okay, so I'm going to specifically talk about that triglyceride form of a lipid. This is the most common lipid found in the body and in the food we consume. As food scientists, you are able to manipulate the shape and structure of a triglyceride to affect certain properties of a food. So we're going to get the basic properties down today. There are two parts to a triglyceride. First is a glycerol backbone. So what I have here in purple is the glycerol backbone. You'll notice it has 3 carbon molecules attached to many hydrogens and some hydroxyl groups, which is the OH group that you see here. So it's a very simple structure. We see that we have carbon, we have oxygen, and we have hydrogen, just like the last slide said we would. So this glycerol backbone is the starting unit to build a triglyceride. The second part of a triglyceride is what we call a fatty acid. So a fatty acid in basic form is a carbon molecule double bonded to an oxygen, then singly bonded to an OH group and an R group. So just like in our protein discussion, an amino acid will change based on the characteristic of this R group. So R is kind of an arbitrary placeholder for what we consider a chain of carbons surrounded by hydrogens. So imagine a chain of carbons represented by this R group. If we look at a few examples of fatty acids, we have 3 here. The fatty acid has its own name and its own properties, its own structural shape based on the carbon chain that was put together. So it's all about the carbons and hydrogen makeup. We have, you'll see here, carbon chains, the first one in the green box, second in the blue box, third in the red box. You'll notice that these all are surrounded by hydrogens, varying number of hydrogens. But again, we have that carbon and hydrogen makeup. And then we have that carboxyl group, that COOH. Okay, so fatty acids will vary in length. We could have a fatty acid that's very short, only consisting of 4 carbons, or we can have a fatty acid that's very long, consisting up to over 24 or up to 24 carbons. So length of fatty acid varies. We see varying fatty acids in plant and animal sources. Plants usually only have around 10 different types of fatty acids. However, animals, we as animals have 20 different types of fatty acids. So there is a plethora of options for linking these carbon molecules together and attaching certain number of hydrogens. So now we can talk, we have a glycerol backbone and fatty acids. How do we put those together to make a glyceride? So I've put our purple carbon chain glycerol backbone plus 3 different fatty acids represented by 3 different colors. When we add the fatty acid to something that has glycerol backbone, we will see a reaction occur to produce a glyceride plus water. So why does that happen? In the glycerol backbone, those hydroxyl groups, those OH groups, are very reactive, meaning they don't have a problem leaving the glycerol backbone and combining with something else. On the fatty acids, we have that carboxyl group, that C, double bond O, single bond OH. That is also reactive, meaning it doesn't have a problem letting go of that hydroxyl group to combine with something else. So as an individual unit, this glycerol backbone is considered polar, meaning it will interact with water in main terms. These fatty acids are also polar because they will interact with water. So what happens when we put fatty acids and glycerol backbones together, they will combine and create a bond between this carbon, oxygen, then carbon, and we lose a water molecule. So this purple H will combine, or this purple OH will combine with this pink H to create H2O, and that means this purple carbon will bond with this pink oxygen, which is already bound to the rest of the fatty acid. Same thing happens with these 3 or 2 other types of fatty acids. So let's say there are different types of glycerides. You've probably heard of monoglycerides, diglycerides, and triglycerides. Remember, triglycerides are the most commonly found lipid in our body and in the food we consume. However, monoglycerides, meaning we only see the combination of this pink fatty acid attaching to the glycerol backbone. So essentially, there are no green or orange/brown fatty acids to combine to the other 2 hydroxyl groups. So that is why it's a monoglyceride, meaning there's only one fatty acid attached to the glycerol background. This molecule is partially polar because we still have these polar hydroxyl groups to combine with other substances in whatever liquid or solid we are making. So that means a monoglyceride and a diglyceride, because they're both partially polar, still can combine somewhat with water. It's not like we see a complete separation of oil and water. This hydroxyl group will combine with some water in a dough that we are making, a food that we are preparing, or a cheese sauce that we are preparing. Triglycerides, again, are the most common, where we see all 3 of these fatty acids combined to the glycerol backbone. And again, that's nonpolar because we have eliminated this hydroxyl group plus these 3 hydrogens to make 3 water molecules. So there is no more oxygen that's really going to combine with water, and that's why we see separation of fat from liquid. All right, so now there are ways to categorize lipids, mainly when we think about those fatty acids, okay? So carbon, no matter if you're talking about food, if you're talking about organic chemistry, if you're talking about biology, carbon will only ever bond to 4 different things. So on the screen, you have 2 carbon molecules. Each one of them has 4 lines coming out of them, meaning they're bonded to 4 different things. 3 hydrogen atoms plus the other carbon, okay? So the question becomes, what if there are only 4 hydrogens to bond to these 2 carbons? That means let's take away these top 2 hydrogens, we're leaving carbon with only 3 bonds, and that will never exist in nature. So carbon will do something to accommodate and bond to something else. It does that by forming what we call a double bond. It will bond twice to the other carbon in this molecule. So if we think about it, a fatty acid chain is made up of many carbons attached to hydrogens, but sometimes we don't have enough hydrogens to attach to all the carbons. So we have to allow those carbon molecules to double bond. So looking again at our green, blue, and red fatty acid examples today, the top one in the green box, that has no double bonds, meaning every carbon is attached to 1 or 2 other carbons and 2 hydrogens. That is what we considered a saturated fat, meaning those carbons are saturated with hydrogen bonds. The blue box, though, we form 1 double bond here in between 2 carbons in the middle. So because this carbon and this carbon are bonded doubly to each other, they can only bond to 2 other things. That would be a hydrogen and a carbon. So we get the double bond. This fatty acid chain we see right here in the blue box is what we call a monounsaturated fatty acid. Let's break that word down. Mono meaning 1. Well, what do we have 1 of in here? Well, we have 1 double bond between 2 carbons. Then we have unsaturated, meaning we are no longer seeing saturation of carbons by hydrogen because we're missing 2 hydrogens like we saw up in the green box. So a monounsaturated carbon or fatty acid only has 1 double bond in its structure. Conversely, when we start to see multiple double bonds formed, mainly 2 or more between carbons, we get what we call a polyunsaturated fatty acid. So again, it's unsaturated because there are not the same number of hydrogens that we would get if it was all singly bonded. And it's poly because there are many double bonds. Okay, so all of these are fatty acids. I have been talking specifically about fatty acids, but remember, fatty acids combine with the glycerol backbone to make a glyceride, most often a triglyceride. So we can categorize lipids, mainly the triglyceride, based on their saturation. So let's say in this, the pink fatty acid is saturated, meaning we have hydrogens bonded to carbons. The green fatty acid is also saturated, meaning hydrogens bound to carbon. And the brown/orange fatty acid is also saturated. So that means this entire triglyceride is a saturated fat. Now, we don't always have to have the same fatty acid bound to the 3 parts of the glycerol backbone. We can have 3 different fatty acids. The first might be saturated, the second might be a monounsaturated, and the third might be a polyunsaturated. That would mean, for the most part, this whole triglyceride is an unsaturated fatty acid, because these two are unsaturated versus saturated. So it's really the character of the combined 3 fatty acids that categorizes triglycerides. Now, why does this matter? This affects properties of fats, and without knowing properties of fats, we as food scientists cannot understand how food will turn out if we manipulate the fat content. So in class, we're going to start to hypothesize what happens if we have the majority of saturated fats versus unsaturated fats in a food source. But for now, I am going to go ride my horse. I hope you also enjoy the rest of your weekend, and I will see you on Monday morning.